squared minus 8x plus 4. Okay. So the rational zero test says that P over Q here's my P value, right? This is P. So plus or minus 1, plus or minus 2, plus or minus 4. I list all of the possible factors of 4, including the negatives. And then here, my leading coefficient is 1. So the factors of 1 are plus or minus 1. And if I take all the possible fractions, so 1 over 1, 2 over 1, 4 over 1, I get plus or minus 1, plus or minus 2, plus or minus 4. Okay? So here I have a list of 6 possibilities. That's the rational zero test. Okay? Now there may be other types of zeros, but if there is a rational zero, it's in this list. Okay? Those are the possibilities for rational zeros. Now let's do Descartes' rule of signs. So we're going to look for sign changes. So I'm just going to copy this again so it doesn't get too messy. So we're going to go P of x equals x to the 4th minus 2x cubed plus 5x squared minus 8x plus 4. So if we look, we're looking for sign changes now. This is positive 1, right? So positive to negative, that's 1. Oops, why do I keep doing that? 1. Negative 2 to positive 5, that's another sign change, so that's 2. Positive to negative, there's another sign change, that's 3. Negative to positive, there's another one, 4. So when I do my chart, I'm going to write 4, but then I have to subtract 2. So I subtract 2 from 4, and I get 2. And then if I subtract 2 from 2, I get 0, and then I stop because I get to 0. So there are either 4 positive real root zeros, 2 positive real zeros, or 0 positive real. So either this, this, or this. There are 3 possible situations.
So if you do it every time, there's like a multiple of 2. So if it was 6, it would be 6, 4, 2, 0.
Yep. Now for the negatives, I'm going to try, I didn't leave myself much room to write, but I'm going to go P of negative x. Everywhere I see an x, I replace it with negative x. So I get negative x to the 4th minus 2 times negative x cubed plus 5 times negative x squared minus 8 times negative x plus 4. And then if I simplify that, I get x to the 4th plus 2x cubed, right? Because this is odd here. So I keep the negative because this is odd. And so the double negative gives me positive. But this is even, so the negative goes away. So this becomes plus 5x squared. Here I have a double negative. That's plus 8x plus 4. Now notice the coefficients of in my polynomial are all positive. So there's no sign change. Which means there are no negative roots, or zeros, I should say. Okay. So that means since they're 0, so if they're 4 positive, they're 0 negative. If they're 2 positive, they're 0 negative. And if they're 0 positive, they're 0 negative. And the imaginary, remember the total has to be what? What's the total number of zeros? 4. So 4 plus 0 plus 0 equals 4. 2 plus 0 plus 2 equals 4. 0 plus 0 plus 4 equals 4. So one of these situations is true. And notice that because there are no negative zeros, remember, this is my possible list right here. Okay? I can eliminate those negative ones because there are no negative zeros. Okay? So by the rational zero test, and Descartes rule of signs, I know the possibilities have been narrowed down to just 1, 2, and 4. Okay, so now I'm going to use synthetic division to test each one of those. Okay.
So 1, 2, and 4 because what?
From the rational zero test, remember we did that up here? You take this constant, divide it by this one, and then you do all your, and then we got plus or minus 1, plus or minus 2, plus or minus 4. But then Descartes rule of signs showed us that there are no negative rational zeros, so I eliminated the negatives. So now I'm just going to test those. So we have 1. I'm going to test 1 first, and my coefficients are 1, negative 2, 5, negative 8, 4. And doing the synthetic division, I bring down the 1. 1 times 1 is 1. Add it to the negative 2, gives me negative 1. 1 times negative 1 is negative 1. Added to 5 is 4. 1 times 4 is 4. Added to negative 8 is negative 4. 1 times negative 4 is negative 4. And you'll see that because I got 0, then that means that 1 is a 0. So my function is x minus 1, right? You take the opposite, you subtract this number, so x minus 1 times, these are the coefficients of my quotient. So this 1 here is in front of a cube. I'm sorry, x to the 4th. So this is the 1 in front of a cube, x cubed. So this becomes x cubed minus 1x squared plus 4x minus 4. And so if I want to test the other ones, I can test this polynomial here, and you'll see that if I test the 2, I get 1, negative 1, 4, negative 4. See how quickly this goes if if you do this.
Wait, why don't you do, I thought you were supposed to do it on the other number 1.
I mean, I can, but if since I pulled this one out, if there's a 0, another 0 for this one, it's also going to be a 0 for this. So you can do either one. Once you found 1, you can just keep working down. Right? But I didn't get a 0 there, so this one's out.
So 2 doesn't work.
Right? And then if I try the 4, you'll see that one doesn't work either. You get 16. Did I do that right? Let's see. 1, 3, 12, 16. 4 times 16 is 64.
So the remainder is anything but 0.
Exactly. So that's out, right? Because we want it to be an exact factor. So my thinking is, because if I go back to the Descartes rule of signs, I got to think this logically. I know I have at least one positive, right? Because I found it. It was 1, right? When I tested 1 and it got 0. So I know 1 is a 0. So I know that this is out, right? Because I know I have at least 1. So it's either here or here. And I have no negative. So I'm wondering if maybe I have a multiplicity here. Because, so let me check that out. I'm wondering if 1 is 0 again. So I'm going to try that. 1, -1, 4, -4. Now I can't use the original one. If I'm testing 1 again, I can't use the original because that's not going to give me any new information. I want to know that I already know that this is a factor of my original polynomial. I want to know if there's another factor lurking in here. So I've got to test this polynomial. So I'm using those coefficients, and you'll see that it is, in fact, 1 times 4 is 4. I do get another 0. So that means 1, not only is it a factor of my original, but it's a factor of my quotient, and therefore it occurs twice. Yes.
If it were a multiplicity of 2, you could take the 1 and the 4 on the bottom and just keep going down. Keep plugging in 1. I mean, a multiplicity of 3, I mean.
You would have to factor out the 1. Once you find one factor, you got to bring it out and do the quotient. And use that next one. Because if you get 0, you won't know if it was from the first one or the second one. You know what I'm saying? You've got to eliminate the first one, get it out of the way. So that's why you got to test the quotient. Is that what you're asking? I'm not sure.
I was just asking, if we thought it was a multiplicity of 3, would we take the synthetic division we just did and plug it in again with 1?
Mm-hmm.
Okay.
But you would have to use this down here, plug it in here, right?
Yes.
So from this point now I know that 1 occurs a multiplicity of 2, so it becomes x minus 1 squared. That's my function. And then what's left is, so this represents a cube, right? This 1 came from this right here. So this is a cube. That means this is a square. So this becomes x squared plus 4. And if I want to find the zeros, I'm setting it equal to 0. Well, we already found 2 from this right here. I mean, 1, 0 of multiplicity 2. Now this, you can see, will give me complex or imaginary solutions. So if I set x squared plus 4 equal to 0 and try to solve that, I'm going to get imaginary. And so I'm going to get x equals plus or minus 2i. So the zeros, 1 is a 0 of multiplicity 2, and then we have also 2i and negative 2i are zeros of multiplicity 1. Because they occur once. So we found the 4, and if you go back to the Descartes rule of signs that we were working on for this problem, I'll let you finish writing, and then I'll go show you what you can see that we have 2 positive, that's the 1 multiplicity 2, and then we have the 2i and the negative 2i, so we have 2 imaginary. So this is the correct situation right here.